Hello everyone, my name is Emani from Western Michigan University, and today I'll be giving a presentation on development of a screen-printed flexible porous graphite electrode for lithium-ion battery. This is the outline of my presentation where I'll be discussing about the energy storage, lithium-ion batteries, charging and discharging of lithium-ion batteries, and various printing process for lithium-ion electrodes in the introduction section. Then I'll be moving to the experimental section where I'll be discussing about material, design and fabrication, and the post-print characterization of the printed electrodes, and the results section where I'll be discussing about the testing the coin cell assembled and the formation results that were obtained, and then the conclusion at the end. What is an energy storage device? It is a device that is used for storing electrical energy and releasing it when required. As of end of March 2020, global operational energy storage capacity totaled approximately 184.7 gigawatts, which included 92.6 pumped hydro energy storage, 5.2% electrochemical, 1.7% molten salt, and the rest 0.4% being flywheel and CIS energy storage. Among the 5.2% of the electrochemical energy storage, 89% is owned by lithium-ion batteries, and the rest 11% comprises of sodium sulfur batteries, lead batteries, flow batteries, supercapacitors, and other form of energy storage. Global lithium-ion energy storage total approximately 8,544 megawatts by the end of March 2020, including its applications across various devices like smartphones, laptops, electronic vehicles, e-buses, portable energy grids, and renewable energy. Let's discuss in detail about batteries. So, what is a battery? It is an electrochemical energy storage device that has two electrodes, namely anode, the negative electrode, and cathode, the positive electrode. Flow of electrons and charged ions between these two electrodes through the electrolyte provides electric current that can be used to work. Batteries are generally divided into two types, primary batteries and secondary batteries. Primary batteries are non-rechargeable. Once they run out of charge, they will be dispensed. Most popular primary battery is an alkaline battery, and these batteries have low performance due to high internal resistance, which determines free flow of electric current through the device. These primary batteries run on oxidation and reduction of the electrolyte with the metals. Since they are non-rechargeable, they are deemed as expensive in continuous use. In order to overcome this limitation, secondary batteries were invented. These secondary batteries are rechargeable batteries. These batteries have reversible cell condition and can be restored by passing current to flow into it. Lead acid battery was the first rechargeable battery invented in 1859. They are cost effective and can supply high surge currents but have low energy density. In order to meet the requirement of higher energy density, new batteries were invented like nickel iron, nickel cadmium, nickel metal hydride, which had higher densities compared to lead acid batteries. Among these batteries, nickel cadmium was the least used due to its toxicity. As the evolution of the batteries took place, in order to meet the higher energy density, lithium-ion batteries came into existence in 1991. Sony launched the first commercial lithium-ion battery in 1991, which has higher energy density and have number of specific cathode formulations for different applications. In today's world, lithium-ion batteries have become most dependable batteries considering their performance. As the demand for energy density keeps increasing, we expect to see commercialization of new batteries like lithium-ion with silver nanowire and lithium air by the end of this decade. So this slide shows the motivation of this work. So before discussing about the motivation, I'll just point out a few points about the lithium metal battery that was first invented in 1970s. Though it had high energy density, it was interpreted unsafe due to its instability. These lithium metal batteries are non-rechargeable. In order to overcome these limitations, lithium-ion battery was invented as an alternative to these lithium metal batteries, which had advantages like high energy density, relatively low self-discharge, and improved safety compared to lithium metal. These advantages have led to the growth in the market for lithium-ion batteries over years. The graph on the right shows the market for lithium-ion batteries from 2016 to 2022, and you can see a growth of 33% over a period of 7 years, and it is expected to reach 75 billion American dollars by the end of 2025. And the market for automotives, which is electrical vehicles, is expected to grow the most, followed by the growth in renewable energy sector. Let's discuss about the charging and discharging of lithium-ion batteries, which tells us the way the lithium-ion batteries function. During charging, as you can see, the lithium ions move from cathode to the anode through the electrolyte. Electrons are pulled from cathode to anode by external voltage. And during discharge, lithium ions move from anode to cathode through electrolyte. Electrons flow through external channel. Power is produced by the flow of electrons through those external channel by external voltage supply. During charging process, when all the lithium ions and electrons are in the anode, the battery is fully charged and ready to use. And while during the discharge process, when the lithium ions completely move into the cathode, the battery is completely discharged and should be charged again. This slide shows us the various printing processes that are out there currently for for fabricating lithium-ion electrodes, ranging from bar coating, inkjet printing, laser patterning of the electrodes, gravure printing, aerosol jet printing, 3D printing, screen printing, and flexographic printing. Before discussing about screen printing, let's just give an overview of the materials that we have used in order to prepare electrode slurry for screen printing. So the active material that we have used is graphite with a particle size of 16 micrometers, and the conductive additive is carbon black C45 with a particle size of 37 nanometers. PVDF is the binder we have used, with the solvent being NMP. And the substrate we have used to coat this slurry is a copper foil with a thickness of 9 micrometers, which is the thickness that is commercially used. So, for the preparation of the ink formulation that was considered was graphite, carbon black, PVDF in the weight ratios of 92:6 with the solid content of 55%. This picture here on the left shows the schematic of the ink preparation where graphite and carbon black are mixed with PVDF, and NMP is added to the mixture to get the required solid content of 55%. The ink is then mixed in a Thinky mixer at 2000 rotations per minute for 6 minutes, which gives us a homogeneous ink slurry. After obtaining the homogeneous ink slurry, the ink is characterized using FTA 200 gyanometer, and surface tension and contact angles of the ink are measured. The surface tension was measured to be around 6.1 dynes per centimeter using pendant drop method, and the contact angle was measured to be around 70 degrees using sessile drop method. These numbers show that the ink has good wetting properties and is screen printable on this copper substrate. So this slide shows us the design parameters of the screen printing that we have used. The screen printer that we have used is a MSP485 semi-automatic screen printer. The image on the left bottom shows the screen printing design, and the right image on the right shows the image of the screen that we've used for printing, which has specifications of 41.3% open area, 27.9 micrometers wire diameter. The mesh count of the screen is measured to be 325 with this thickness being 66 micrometers. The emulsion thickness of the screen is 45 micrometers, and the theoretical dry print thickness is expected to be around 41 micrometers. So in this slide, you can see schematic of the screen printing on the left, where graphite ink is put on the screen, and the copper substrate is placed on the platen and vacuum, so the substrate is completely flat. We use a squeegee to push the ink from the screen onto the substrate. And as you can see on the right, the image on the right shows the screen printed graphite ink on the copper substrate. Since it's a screen printed electrode, it is flexible as well. After getting the printed electrode, we have performed post-print characterization of the electrode using Bruker, and we have measured the thickness and roughness of the printed sample. The thickness was measured to be around 40.6 micrometers, which is close to the theoretical dry print value that we expect to see, and the roughness is measured to be around 2.9 micrometers. In order to assemble a coin cell battery, we punch out a coin cell from the printed electrode, and the mass loading was measured to be around 3 milligram per centimeter square. And the punched coin cell is calendared in order to enhance its performance. The porosity is controlled at 35% for calendaring the coin cell. This slide shows us the assembling of the coin cell battery, where we use a negative case cell, a spring, and a spacer on top of the spring. And then we use 1 drop of electrolyte, which is LiPF6, and a lithium foil, which acts as anode, and 3 drops of electrolyte, and a separator, which makes sure that the anode and cathode don't come into contact with one another 5 drops of electrolyte, the graphite electrode on top of the separator, and a spacer in the positive cell case. The spacer at the top and the bottom make sure that all the electrodes and the separator are aligned properly over one another. The assembling of the coin cell is done inside an MTI glove box, and once the assembling is done, the cell is placed inside a coin cell crimping machine and it's punched to make sure that the coin cell is completely sealed. You can see the assembled coin cell image on the left. After assembling the coin cell, it is connected to a battery tester using coin cell clamps. The battery tester we have used is a LCD2001, a 5 volts 5 milliamperes tester, which is connected to a PC with RAM BTS software installed on it. The formation results of the battery were tested at a C rate of 0.1 C, which means that each cycle is run for 10 hours. We run the results for 3 cycles, which means that the formation results of the half cell is run for 30 hours in total with rest time in between them. From the formation results, we expect to see the first charge capacity of the battery being close to the theoretical capacity of graphite. The theoretical capacity of graphite is around 370 milliamperes per gram, and the first charge capacity obtained is 356.2 milliamperes per gram, which is what we expect to see. So as conclusion, a flexible graphite electrode was fabricated using screen printing. Half cell was assembled to get the formation result for the electrode at a C rates of 0.1 C, and the first charge capacity was measured to be 356.2 milliamperes per gram. The rate test will be performed at different C rates from 0.1 C to 6 C for future work, and capacity retention will be measured after multiple cycles at higher C rate. Thank you, and I'll be happy to take any questions you have.